Thanks very much. We are going to start the afternoon session uh, of the workshop. Terry Brennan will be the moderator for this section, and he'll introduce people in just a moment. For those of you who are both in the room and online, we'd like to encourage you to use the Twitter handle, the hashtag IndoorPM, all run together. If you'd like to make comments on the proceedings, we already have some of those up online. And with that, Terry, please.
Thanks, Dave. I'm my name is Terry Brennan from Cam Road and Associates. Uh, no further introduction. I, I would like to introduce the first speaker in session number 3 on exposure and characterization. The first speaker is Barbara Turpin from University of North Carolina. Please take it away, Barbara.
Thank you. It's a pleasure to be here. Happy afternoon. Let's see. I guess I'll use this, and I have a pointer. I do. Okay, I'm going to limit my comments today to fine particles, so PM 2.5, and I'm going to both use measurements to provide evidence for the things I'm going to talk about, as well as predictions. You've seen a house several times, so I'll just show it one more time. But the indoor concentrations of fine particles, of course, are a balance between sources and sinks, and those sources include indoor emissions of particles and outdoor to indoor transport of particles. The sinks, of course, include deposition of particles to indoor surfaces, filtration in air conditioning units, and in heating ventilation systems, as well as exfiltration of particles. Chemistry and partitioning also affect the concentrations of particles found indoors. So with outdoor to indoor transport, if you change when the conditions change between outside and inside, there can be phase changes with outdoor to indoor transport. For example, if the temperature indoors is higher than outdoors, then when you bring in particles that that particulate matter has a certain mix of compounds in it with different vapor pressures, and when they encounter a higher temperature, the vapor pressures go up and some of that material will volatilize. Of course, the opposite can happen. The temperature indoors can be lower than outdoors, and you can get condensation of vapors on those particles and an increase in PM. Charlie and others have talked a little bit about chemistry that happens indoors, and that can also change the vapor pressure distribution of the gases and particles, leading to the formation of new particulate matter and sometimes probably evaporation of materials, both from the particles and from the surfaces indoors, other surfaces. Charlie showed a little bit more of this data than I'm showing, but this is from the RIOPA study. And in this case, I'm showing New Jersey outdoor PM species composition and the indoor PM composition for it's more than 50 homes in New Jersey. And I, again, want to point out that indoors, the concentration of organic matter in that particulate matter is more than twice as much as you find outdoors in the same homes at the same time. And so that's a lot different than everything else. So for sulfate, the indoor concentrations are lower. For soil, they're lower. For EC, they're lower. And I'll talk a little bit more about other later, but we didn't measure nitrate. And so that other is mostly nitrate in water. In New Jersey, the nitrate isn't very big, but I'll show you California in a little while. So this additional organic matter has to be coming from indoors. It's either emitted indoors or it forms indoors through phase changes or chemistry. In the case, so this is the same RIOPA data. Actually, it's for all 3 cities in Los Angeles County, Houston, and Elizabeth, New Jersey. And so it's more than 150 homes. And here I'm showing the paired indoor concentrations versus outdoor concentrations for elemental carbon and sulfate. And so you can see for the most part, outdoor sulfate concentrations are higher than indoor concentrations. And that's also true for the most part for elemental carbon, although there are homes where the indoor concentrations are 1 or 2 micrograms per cubic meter higher than the outdoor concentrations, telling you that there are some indoor sources of elemental carbon in some homes. So 1 or 2 micrograms per cubic meter. This is the same kind of plot, but for organic carbon. And my group is very careful about sampling artifacts, so we think these are pretty good estimates of particulate organic carbon indoors versus outdoors. These are concurrent measurements in homes. And in this case, you can see most of this is the 1-to-1 line, and most of the data falls above the 1-to-1 line. And there are many homes with 10 or 20 micrograms per cubic meter more organic particulate matter indoors than outdoors. So that's a lot of mass. If we do the very simplest thing and we say all of that outdoor PM comes indoors, there are no losses, okay, very unrealistic, but there are no losses with outdoor to indoor transport, and there are no losses of organic particulate matter once you come indoors, okay? We can get a lower limit for how much of that indoor organic PM is of indoor origin, and that's about 40%. So that's a lower limit, right? If we do a much better job, either by regressing the indoor PM, regressing indoor on outdoor, and finding the portion of that material that can be explained by outdoor origin, or if we use a mass balance model, we assume a P, a reasonable P, we fit K, and then we calculate what the PM of outdoor origin is. We find that about 70% of organic PM is of indoor origin for the typical home. I'm going to skip this. Here's the case for nitrate, and this is Los Angeles Basin. Well, so for Southern California, nitrate is a major portion of outdoor PM. And so you can see here, other, which includes nitrate, but probably isn't all nitrate, is much larger outdoors than it is indoors. 6 micrograms per cubic meter outdoors, 2 indoors. Whereas everything else is kind of boring, or you already know about it in this plot. So Charlie mentioned Melissa London's work. She worked with Suzanne Herring, and they have an unoccupied home in the Berkeley area. How do you do that? Sounds expensive to me. And they measured in real time particulate nitrate outdoors and indoors. They measured air exchange rate. That it was a very nice study. And it turns out it's really difficult to get particulate nitrate from outdoors to indoors. And that kind of makes sense because nitrate is semi-volatile. It exists in the particle phase in equilibrium with gas phase nitric acid. And so when you try and bring indoors gas phase nitric acid and particulate nitrate, you can get the nitrate indoors, but the nitric acid gets scrubbed, okay? Either it can't make it through the building envelope, or if it does, it sticks to the walls once it gets there. And so once you've removed the nitric acid, the ammonium nitrate needs to re-equilibrate. And how does it do that? It evaporates, right? And so if you, at a typical air exchange rate indoors, only the fraction of outdoor nitrate that penetrates and persists in indoor air is very small. It's about 12%. So if you use the measurements then of outdoor and indoor PM, and to give you estimates of the fraction of outdoor PM that gets indoors and remains suspended. So the fraction of outdoor PM found in indoor air, you'll find estimates like this. And so I guess the point I want to make is that the fraction of outdoor PM that you find in indoor air varies a lot depending on the PM species. Okay, and this is just for PM 2.5. But you can kind of understand it. Fine soil dust, okay, it is smaller than 2.5 microns, but not much, right? This is big stuff. And so its losses are large by deposition. Whereas sulfate, if you look at the sulfate size distribution, you see that it's smaller and it's in the size that penetrates pretty easily. And then nitrate also has very large losses. And so my point by showing you this is to tell you that when you bring outdoor PM indoors, the composition of that PM changes a lot. And so if I use the measurements and these F values to inform that, I can look at the RIOPA data, breaking it apart. So if you take the indoor measurements of PM composition and you break them apart into that which is of outdoor origin, so I've taken the outdoor PM and brought it in with those differential losses, it now looks like this. Okay, and then the difference between that and what we measure indoors looks like this. Okay, so the point I want to make here is that indoor PM of indoor origin is organic. And this is New Jersey, and this is California. And I'll tell you that the largest error in these plots here has to do with my assumptions about nitrate. So in making these plots, I assumed all of this stuff called other is nitrate. And I know that's wrong. Some of it's water, I know. And if it's not all nitrate, then it turns out this slice of the pie over here, this 15% is smaller. And the slice that's organic is bigger. Okay, so this in a sense is a lower bound mean for the percentage of PM of indoor origin that's organic. A lot of it's organic. Okay, we can also use prediction to tell us what we have and what will happen indoors. And so my student Natasha Hodis took a good look at the outdoor measurements. You know, PM, total particulate matter, its size distribution varies because it varies with the source mix, and it varies with the composition. But if instead you look at the size distribution of each species itself, it doesn't vary as much, right? And so she looked at the outdoor measurements for species resolved size distributions, and applied to them then loss rate coefficients from Bill Nazaroff's group. So she accounted for the species resolved size distribution, whether windows in the RIOPA homes were open or closed, which we knew, air conditioning losses through filtration, variations in air exchange rate because we had measured that, variations in composition from day to day, phase changes for nitrate, but not for organics. And then she could use the outdoor measurements and the measured air exchange rates to predict what the indoor composition should be using mass balance. And so then this shows the model prediction versus measurement, the modeled in blue, for sulfate, for indoor sulfate, indoor elemental carbon, and indoor organic carbon. So if all the sulfate indoors was from outdoors, and if we did a good job, then these two distributions should match. And when, let's say, when we actually account for windows, when windows were open and when air conditioning was used, the agreement is really quite good. The same for elemental carbon. The agreement is really quite good for predicted indoor concentrations, predicted from outdoor concentrations, compared to measured indoor concentrations. For organic carbon, it's not so good, okay? And I'm not really worried about this because I know there's a lot of indoor generated organic carbon, okay? So a lot of this difference is for that reason. Some of this difference could also be from phase changes, or because we got the model wrong. That's also possible. Okay, so we want to use this model. We did a little bit more work actually to figure out how much of that organic carbon we could account for. You know, how much of that organic carbon was actually from outdoor to indoor transport, and, you know, how good did the model do? But in any case, we figured that we've used data to validate, at least in part, this model. Now we can use the model to say something. And so what we've done here is to take the bar on the left is the composition outdoors. And so in this case, it's the outdoor composition that is typically seen in the northeastern US. And that's a very broad statement, but I hope you'll accept it. And this is the composition seen outdoors in the Southwest in California. And this is a near roadway composition. And we've taken the northeast mean and then enhanced it for organics and elemental carbon near roadway. What if you take that composition then and you bring that material indoors? What is the effect? And so you can see, for example, in the Southwest, this blue is nitrate and it gets much smaller. Okay. When you bring that material inside, let's compare. This is a typical air exchange rate, and this is a more typical of a low-income home. And so when you bring, if you have a low-income home near a roadway, your infiltration factor, or the fraction of outdoor PM that makes it indoors and remains suspended, is about 60%. And it's a little more than half that if you have let's say, a suburban Southern California home. And so there's quite a bit of variability in the fraction of outdoor PM that makes it indoors. And I guess that's the point that I wanted to make in this exercise. There also is a great deal of variability in the effect estimates for outdoor PM health effects studies. So this is Michelle Bell found that the increase in respiratory hospital admissions per 10 microgram increase in PM was smaller in the Southwest than in the Northeast. So certainly some of that difference could be because the composition of the aerosol is different in the Southwest than in the Southeast. Some of that difference could be exposure error, because what we're doing is we're measuring the PM outdoors. We're not measuring it indoors where people are, and the fraction of PM that gets indoors is different in different places. This is a very nice study Charlie Weschler was involved in, Chen et al., where they looked at what happens if you account for that variable fraction of ambient PM making it indoors in your health study. And they did find larger effect estimates, better model fit, and less intercity heterogeneity when they accounted for F. Okay, I want to provide a little bit of evidence for changes in gas particle partitioning with outdoor to indoor transport. So I'm going to use PAH measurements from the RIOPA study because we measured both the gas phase and the particle phase. And so this shows the gas particle partitioning versus the vapor pressure of the PAH for homes from all three cities. And so you can see that the fraction that's in the particle of the PAH that's in the particle phase decreases as the volatility of the compound decreases. That makes sense, right? But there's a lot of scatter in the data, okay? And a bunch of this scatter can be accounted for by changes in temperature going from outdoors to indoors. We do this regression here. And also by changes in carbonaceous aerosol concentrations as we go from outdoors to indoors. And if we account for those then, so here's the measured outdoor for chrysene, a fraction of chrysene in the particle phase, and here is the measured indoor. And if we account for those effects, we see the bar here. So we're pretty close. We're very close for benzoate, anthracene, pretty close for chrysene. The change in temperature with outdoor to indoor transport actually decreases for the homes we had, decreased the fraction in the particle phase. And the organic and elemental carbon found in the extra OC and EC found indoors increases the fraction seen in the particle phase. These are for PAHs for which we're convinced there were essentially no indoor sources. So we should be able to understand their outdoor to indoor transport should be causing these effects, these changes in partitioning. We'd like to understand their organic matter indoors and outdoors. Organic particulate matter is comprised of thousands of compounds. We just measured pHs because they're easy, right? And so for this complex mixture of organic materials, what happens? So we've used thermonuclear AMS measurements from outdoors, and we can understand something about the volatility distribution of the organics. So here's all of the organic matter. The stuff in the open bars is in the gas phase outdoors of our RIOPA homes, and the stuff in the solid bars is in the particle phase. When you bring that inside, then the temperature changes. When you bring that inside in the organic matter, the concentrations of organic matter, or particulate organic matter indoors, are much higher, right? And that both of those things change the partitioning of this stuff that we're bringing in, of the gases and the particles. And so when we do that prediction, here's what we find. For Los Angeles, Elizabeth, and Houston, the part of the bar in red represents homes for which there's an increase in the organic mass of that mixture that came indoors. There's an increase in the fraction that's in the particle phase. And in blue, there's a decrease in the fraction that's in the particle phase when you bring those organic gases and particles indoors. Okay, and so it does go both ways, and it depends on where you are. Houston, there's a lot of air conditioning. Okay, so I haven't left enough time really to talk about the really new stuff, but we all know that VOCs are present indoors in really high concentrations compared to outdoors, and we know there are oxidants. You know that already. What we've been doing most recently is measuring oxidized VOCs indoors, so water-soluble gases indoors. And so we've measured the outdoor concentrations of total water-soluble gases in 13 homes and the indoor concentrations, and they're much higher indoors. So what is this stuff? We're working on figuring it out now, but I predict, that we will find all of these compound classes present in indoor air in the gas phase. And I predict that because we find them when we study the chemistry outdoors, okay? And that these things will partition into water on the surfaces everywhere indoors and into water and airborne particles. They're going to react, and they're going to form things like this over on the right. So they're going to form the chemistry in those wet surfaces is going to be oxidation chemistry. It's also going to be acid catalyzed chemistry or nucleophilic chemistry. And we're going to form some interesting compounds. Okay, and since a lot of homes are damp, this will happen in a lot of places. I've moved to a nice place to study damp homes. I'm in North Carolina now, and I've found out from my friends and colleagues that you have to make sure your air conditioner cycles on and off every so often. It doesn't matter what the temperature is, but during the humid half of the year, it's got to cycle on a regular basis or you're sunk. This is just one more slide here, talks about, these are common water-soluble gases found in outdoor air, and their lifetime in the aqueous phase with respect to OH is really short compared to their gas phase reaction lifetime with respect to OH. So we think that they have high Henry's laws constants. They're going to get sucked up into water. They're going to react much faster in the water. And we know they form secondary organic aerosol, the ones where I've said yes here. And in some cases, they form oligomeric compounds as well. Okay, I think I have to stop. Thank you.